Never what did record that. Okay, here we go. So I'm not going to repeat everything, but let me go back and show the highlights. Sorry about that, folks that are watching the video. We're on Pkt5 class number 20. I forgot to record it, so I'm telling them now. This is the homework that I checked today. Virtual kids, yours is due Monday at 11:59 p.m. on Canvas. You have in-class kids, don't turn it in because I've already looked at your problems. And then we talked about the front of 5.8. What we did, I posted the key now in the screenshots. It's also posted in the comments underneath the sheet on guide 2 of the Facebook. Here's the work we did yesterday on number 3. And then we just got finished. Unfortunately, I worked that one and explained it. But that's what we just got finished doing. We drew some ghosts. This is an inelastic collision. I drew a green ghost, and then I drew the resultant ghost, and then I redrew the resultant where it really occurs, the actual momentum vector, and that's the red one. So that's what we've done, and I forgot to record it. Now we're back to business here. Number 5 is homework. And it's a hard 5, we're gonna work 6. 5 is harder. Well, that doesn't seem fair, except that on the homework, I'm gonna give you 3 dinos. If you're watching this one, you were in class. A lot of people were gone today because of sports. So if you're an in-person student, you get 3 dinos for this one on Monday. But not to leave you hanging, there is a silent help video. It is available, and I will post that in the comments underneath the screenshots. It's also in the YouTube channel, of course, under the 2D collision playlist. And I think it's also probably in the comments underneath the sheet. So it'll overlap. It will overlap number 4. It's okay to overlap stuff. But let's work number 6 together. 6 is like, there's one, I know there's one on the take-home test like 6. Take-home test you'll get Monday. It'll be available Monday evening by 7, I think. And then I'll pass out a paper copy of it, and it'll be available on. The PDF will be available on Canvas, and it'll also be available on Facebook Monday night. More about that. But anyway, so there'll be a problem kind of like this on there, I think. All right, so this is advanced glance ball. Let me show you glance ball, okay? Let me show you glance ball. I'm going to share a different screen. Stop that sharing. And I'll show you 30 seconds worth of our glance ball from today. I think. It's on my basic advanced. Thought I had it. Hold on, Finder. Why wouldn't my video, my picture? Oh, there it is. There it is. Got it. Okay, photos. Boom. Okay, and let's go to photos. Boom. All right, so here is the, you can see this now. Here is the glance ball from this app this morning. Okay. So Brittany is going to be the setter.
Oh, we're going to set it here. We're going to push it over there.
And over there, Carlos is the pusher. And they're trying to hit.
We're going to hit these points.
They're trying to hit those. They're trying to glance the discs off each other. These are hover discs, so they don't, friction shouldn't be a. It's kind of like someone, I had a Canadian, Dr. Fournette did it, and he said it's a little like, you know, he's Canadian, right? So it's like, what's that thing? Curling. It's like curling and air hockey combined. So you're trying to bounce off each other, and then after the glance, it hits one of these. We've been developing this game now for 15 years. This is our rules. There's all these other rules about where they can hit and all that, but I'm not going to bore you with that. If they knock over the rocket, that's even more points. So you get up to 22 points bonus on this. If you guys want to come up next week and try it.
Okay, just had a team knock over the rocket. All right, ready whenever you're ready.
Okay, so Brittany's going to do the set.
The line there. Okay.
She has to stay behind the line. That's the fault line. So technically speaking, she faulted a little bit, but I'm not going to be upset about that. And then Carlos waited. She did a fast set. That was hard. Carlos then has got to glance that thing and hit it, and then not just hit it, but glance off it.
Hit.
Oh. So now either one can glance into the points.
And
all right, so they got 4 points there. So you get 2 shots at it. They ended up, most of them I got today, I think, was 13 points. You get 2 points for trying. All right.
4, right? Okay, that's not bad. Okay, so
everybody took their turn. All right, stop that sharing. So that is glance ball. It's kind of fun. Sometimes we do Final Four and we do class versus class and all that stuff when we have more time. This time we just got to give it one shot at it. Okay, boom. So back to this. Now this problem we're going to work is advanced glance ball, and we'll do that in AP physics. In advanced glance ball, you put a disc weight on one of them, so it makes it double the weight of the other. That makes it even harder. It's like if you play pool, your cue ball weighs the same as the other balls. It's magnetic. The cue ball is magnetic at a bar, so it knows to go to the return for you in case you scratch. But it's the same mass, pretty much. It's the same mass as the stripes and solids. But advanced pool would be that the cue ball was twice the mass, not twice the size, twice the mass, twice as dense as that. That'd be a hard game to play. Anyway, so this is advanced glance ball. It doesn't say how much these things weigh or what their mass is, but I have FAI coming in. So sorry, MA coming in initially, and it comes in and gets hit by mass B sliding along, and then A ricochets off this way. It's elastic collision. So this is a lot like number 3 on the front, only we're not going to have to worry about all these numbers and sines and cosines and calculators and all that. Okay, so just all it says to do is, it just says draw what PBI would look like. This would also be a case of if you are, say you're a police officer or highway patrol or something, and 2 things hit and they bounced off each other. I don't know what you'd have, but you're trying to figure out, well, what was the mass B doing before the collision? What direction was he going? So a cop would look at a wreck and see the after effects, and from there try to reverse engineer it and see which car was speeding or what direction. This guy says he was going north. Was he really going north? So let's say this person B said that their elastic car was going north. Are they telling the truth? All right, so here we go. We are still recording out. All right, here we go. I'm going to erase this, give me some space here. So we start off with, and I added this about 5 years ago because kids were getting confused as to which arrow they would just add them up as they are. You can't do that. You have to first do some manipulation a little algebra. So we're going to use conservation of momentum. And so I'll keep the colors, and I fortunately picked green. And since then, I wrote this about 10 years ago. And since then, now I use green for ghost, but I didn't have that convention back then. Tell you what, because this is for real here, this is getting taped. I'm going to make the A blue. Make it blue so I can stay with my green convention. So A is now blue, and green will be ghosts. Okay. Oops. A is blue. Comes and goes. Okay. So let's write the algebra here. We know conservation of momentum, so we have PAI plus black plus PBI equals, this is just, you start off with this, equals PA final plus PB final. All right, so that's conservation of momentum. Well, I'm doing a little algebra here because I want to know what is PB. I want to know what is PB final, right? Sorry, I want to know PBI. I want to know this. So I got to subtract PAI from both sides. I know it seems obvious, but still, trust me, on tests, you need this kind of helper to make sure you don't flip the wrong thing. So, okay, so PBI is what I'm solving for. PBI, and I have PAF, PBF. Those I don't change, but I subtract PAI from both sides. Okay, so that tells me that this. Let me blow this up a little bit so you can see it. You look at my phone; it's kind of hard to see it if you're on your phone. So that's my game plan here. I'm going to add PAF with PBF, and then I'm going to add the opposite of PAI. That's minus, add the opposite. So I need to, before I forget, go turn around PAI. That's all we do. Remember, when you flip the arrow, make a negative, you flip the arrow. So I'm changing the arrow to go that way, and so I don't screw up here. Let's go ahead and kill that arrow over there. Get that arrow off there. Okay. So now all I got to do is add those three vectors up and find the resultant. Well, I can use any, I can add them in any order I want. I did 3 different orders for all 3 classes and got the same answer. But let me go ahead and do it this way. I'm going to leave PBF alone. I'll slide PAF over and I'll slide PAI up. So I'm going to first draw the lines of action. Trust me, yeah, there's still some stuff you got to do, but it is easier than doing all that stuff we did yesterday. So I'm going to draw a line of action on PAI, and I'm going to, anything I slide, I got to draw a line of action on. And that's mostly just to help my eyes, because I don't want to have to go back with a protractor. I'm trying not to use a protractor. It's being lazy, I guess, but you can get a pretty good answer this way. Remember, head or tail, you're getting a ballpark, back of the envelope, 1 sig to 2 sig answer. All right, so, okay, I'm gonna first slide PAI. So I just gotta recreate it. You do this while I'm doing it. 9.5, 9.5, okay. 9.5, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is PA. Uh-oh, my bad. That is a ghost. Lost my mind. Not a real vector. So that is the ghost of PAI. PAI. Okay. And then I'm going to draw the ghost of PAF, but I gotta be careful that emanates, it's head to tail. So I don't want to put it up here. That'd be tail to tail. So I take it and I'm going to move it right to there. So it's coming from the tail of it's coming from the head of PB final. Okay, get my length right. 1, 2, 3, 4, 5, 6, 7. If you're on an iPad, you could just cut and paste, I suppose. Green. 1, 2, 3, 4, 5, 7. All right. That is PAF. It's ghost. All right. So the resultant, it's mathematical. That goes from the very beginning to the very end. The very beginning is right here. Boom, boom, boom. Very end's right there. So let me draw that. And that's going to go, the arrow though is important. It's that way, very beginning, very end. That's my R. But at this point, I would get a, I don't know, 7 out of 10. So now I take that R, and that's going to be my initial vector, my initial momentum vector of B. Boy, howdy, look at that. So I'm going to make PB just, let me just make it dark red. Dark red, like that. So I'll change this. I put the dashes in there because when I print off the sheets, they're not in color. So they can distinguish. Okay. So this tells me a PBI, 1, 2, 3.5. Looks like this. Boom, boom. That's it, folks. So the person said I initially was going north, they were lying. Because this reverse engineering everything tells me that no, you were going north, almost due east, and you hit. So the PBI comes in, hits, and bounces back almost straight back. The PAI comes in, hits, and looks like, and also, but not only that, the B object must double its velocity. Its mass didn't change. The arrow got twice as big, so it doubled its velocity. PA didn't really change its velocity a whole lot. Looks like it slowed down a little bit, but it definitely changed its direction. So you're looking at collisions, you're figuring out, but this, so you think, well, so what? Except that this is what Max Planck used to start to understand black body physics, black body radiation, where it's particles inside black boxes bouncing off walls and stuff. And as they bounce, they use conservation of momentum. He assumed elastic bounces. And from there, determined black body radiation, had this catastrophe, as they say, and that started the quantum revolution. So this stuff is not trivial. Everything we do in here is foundational. You're not wasting your time. There you go. That's done. We're done. So 5 then is for homework. Try that, but please watch the silent help video, which I will post in the comments, and then that finishes 5/8. So you're going to do this as long as you have it all done and turn it in by Monday night. You're fine. It'll be worth a lot of points. I'm telling you, it's probably worth like 30, 40 points. So turn that sucker in. All right. Then we play glance ball, and I talked about glance ball already. And then the last thing we did, we came back in the room, and we're starting now to get ready. This is the last thing we'll do. We got about a 15-minute little talk here, and we're talking about the introduction to duck walking, so here's how it goes. So we'll do this introduction. That'll lead us to something called Hooke's Law. That'll lead us to the duck walk lab. The duck walk lab will lead us to forces and how they're applied and accelerations and masses and Newton's second law. And then that'll lead us to free body diagrams, which is probably the end of next week. And then we'll be on free body diagrams off and on the rest of the year. And then that'll lead us to work, which leads us to energy, which leads us to power, and torque and stuff like that. So this is a springboard here. Okay, so you'll need your notes. You need to take some notes here. So get out your notebook paper or your iPad, whatever. Let's take a few notes. I'm gonna start off with this. CEIINOSSSTTUV. Now that is a anagram. And it's probably the world's most famous anagram, historically the most famous anagram in history. This is, so what they did back in the day, back before patents and all that and copyrights and all that, when a scientist, when a physicist or chemist or something, there really wasn't chemistry so much, there was barely physics, but when a physicist or somebody, and really even Newton was considered a natural philosopher, but when a scientist, let's say, would come up with a new idea, they wouldn't go out and get a patent on it. They would instead, to claim credit for it, original credit, they would send out cryptic notes, sometimes in the form of anagrams. And these anagrams are based on Latin, most of them, because Latin was the language, the universal language. Okay, so it's important to learn some Latin so you know kind of base roots of words, especially if you go to med school. But anyway, so they would send out these anagrams encrypted. As you know, an anagram is the name of something, but all the letters are all mixed up. So normally in an anagram, typical procedure is go alphabetically and just list all the letters that are in the word. So this was the most famous one, sent out by a guy named Robert Hooke. Robert Hooke, and I'm buffering for some crazy reason. Robert Hooke. Robert Hooke in about 1690, somewhere in there, give or take 10 years. Robert Hooke. So he's a contemporary of Einstein, of Newton. So he was a rival of Newton, Isaac Newton. So he sent this out, and I'll explain that in a minute. Let's go back to Newton for a second. So when Newton first, and I have pictures of all this stuff, I didn't think I'd be presenting today, and I didn't have time. I rushed home, ate some quick lunch, and came up here and gave this. So I'll either put these in the screenshots or I'll probably put them in the screenshots this afternoon. And then I'll talk about them a little more on Monday. But because it's historically, you got to understand where we're coming from on this lab. Okay. So Robert Hooke sends out this encrypted code to claim credit for this new law he had discovered, new physics law. The reason why he was claiming credit, because he's afraid that Isaac Newton would take the credit from him. Isaac Newton was a much younger man, but they were still contemporaries and they were rivals. Robert Hooke was with the Royal Society. He was the curator. He was, and the Royal Society was the first really science society, still around. It was the first science group of learned men. There was no women in it. In the 1600s, started around the 1600s. And so he was the curator. He was in charge of all the equipment. Because I have Nullius in Verba. Nullius in Verba. I believe it's it was Ian, I think, in Verba. This is above my door. I haven't looked at it in a while. anyway, so that means this was the Royal Society's motto, and it means not by word of mouth. So, meaning that for the first time, excuse me, some kind of hay fever. For the first time, scientists, quote, scientists were going to actually check and see if something actually worked, if it was true. They're really their goal was to understand truth. And before that, it was Aristotelian logic, which was basically somebody would sit around and philosophize and say, this is why things happen, but not really experiment. Except for Galileo rolling balls down ramps, not many people actually did any experiments. They didn't want to get their hands dirty, right? That was beneath them. So the motto of the Royal Society was nullius in verba, which meant not by word of mouth, meant that we are going to actually do. So that's above my door in my classroom. I try to just tell you stuff. Of course I do here, but we actually do something. Okay, so all of that taken into account. Now here comes, as a young man, Isaac Newton comes to the Royal Society at 21 years old, not much older than you. And he'd been studying Einstein as well. Isaac Newton was obsessed with light. That's all he thought about for a while. That sounds exactly like Einstein, right? That's why I get him mixed up. Einstein, when he's younger and a teenager and 20s, was obsessed with light. And so was Newton, even as a 7-year-old, 8-year-old. So Newton studied light, and he's the first guy. You know that Pink Floyd album? I'll include it in the screenshots. I'll include all the Pink Floyd. Made note to myself. This famous Pink Floyd album with the light coming in, hits a prism, then bends into all the colors. The color spectrum. It was Newton that came up with that. And so as a young man, he studied optics, the first person really to seriously study optics. I mean, Galileo used optics in his telescopes, but Galileo didn't understand optics. It was Newton that figured out optics, refraction, diffraction, reflection of light. So he presented that to the Royal Society as a 21-year-old man. Well, Robert Hooke was sitting in the audience as an older, he was probably 10, 15 years older, and he sort of snickered at Isaac Newton, because Robert Hooke tended to take credit for everything. Like, oh, I already thought of that. I'm in charge of prisms. I'm in charge of it. So he kind of snickered, like, who is this young whippersnapper coming in here telling us men about something, trying to teach us something? And Newton heard that snicker and looked up and locked eyes with Robert Hooke. And from then on, Robert Hooke was his sworn enemy. Newton never forgot a slight. It's a little like Trump in that way. Trump, he'll never, if someone crosses him, he never forgets, right? And that's the way Isaac Newton was. And he was petty. Got to admit, even if you're a Trump fan, he's petty. And he was that way as well. So he, Isaac Newton, and I'm not going off, I actually talked about this in class. He kind of became, like I said, the sworn enemy of Robert Hooke. And anytime Hooke would bring something up, Newton would try. And Newton became more and more popular, more and more political, and eventually became the president of the Royal Society. And so when Robert Hooke, who had the misfortune of dying first, when he died, they were moving, at the time, they were moving all the stuff over to the new building that the Royal Society was going to. And my wife and I went to London. It's in London. And I got to stand in front of the new building. It was obvious that the Royal Society is pretty cool. Rather nondescript building, but I know all the history of it. It's pretty cool. So when they moved everything over, they're moving all this equipment over, and they had all of Robert Hooke's stuff in the basement and all of his, paintings. He was a famous guy. I mean, Robert Hooke was, look, man, I'll put some stuff in there. He wrote this book called Micrographia. It was a bestseller. He's the first guy to look through a microscope. I mean, Galileo was the first one to look through a telescope. Robert Hooke was to flip that around and look through a microscope and looked at plants through a microscope, and he saw these little, looked like what he called cells, like what a monk would be in at a monastery. And so the name sticks. You still use the word cell in biology. Everybody back in those days had fleas. Fleas were everywhere, right? I mean, it's the source of the plague. And so people didn't know what they were. You couldn't really see a flea very much, a little tiny dot, basically. And they wouldn't know how can these fleas jump so high? Well, I'll show you the pictures here later on. When Robert Hooke was also a great artist, a great drawer, he drew fleas from what he saw in his microscope, and you could see the spring action of a flea. People all had head lice back then, right? They wore wigs, they shaved their heads because they got head lice, right? And so they wanted to see, how are they so hard? How are these lice, these things that are in our hair, why won't they get out? Have you ever had head lice as a kid? Elementary school, they're a pain to get out. You had to get a special shampoo, and you cannot, it's awful. But this was a daily occurrence. Everybody had head lice. And so he's the first one to draw head lice. And so he was like famous already. And then half of London burnt down, and he was the architect that built it back. Have you ever been to London, been to Piccadilly Square? He's the one who designed all those places. So he's a Renaissance man. He was an astronomer. Anyway, so all this stuff. Well, when he died, instead of honoring him, what does Newton do? Petty man that he is. He says, I'll move all of Robert Hooke's stuff to the new building. He then, once everybody left, took Robert Hooke's paintings of Robert Hooke and burned them all in the lawn. So there's no recollection of what Robert Hooke looked like, because all the paintings of him were burnt by this petty man, Isaac Newton. The only description we had of Robert Hooke was by Isaac Newton, who described him as a hunchback, bug-eyed, balding old man. And so sometimes you'll see drawings of Hooke, he looks like Igor. Other people have other recollections, and so they've looked through historical and they try to paint what they think he might look like. So no one really knows what Robert Hooke looked like. Okay, all of that that's what Robert Hooke's dealing with, is this crazy Isaac Newton. And he's got to kind of watch his back all the time. So he sends out his new information with that anagram, okay? And nobody could undo it to understand what he's saying. So at a Royal Society meeting with Newton present, he unveiled it, and it's this: Ut. This stands for Ut Tensio Sic Vis. Anybody here in Latin? If anybody's in Latin, you might recognize that phrase. It's a very famous phrase. You can look this up, and it'll talk about Robert Hooke. Ut tensio sic vis. And this means, this means a couple of ways to interpret this, but this means as the force, so the tension. That's one way of saying it. And sometimes people say, instead of tension, they say stretch. As the force, so the stretch. That's sort of a modern day way of saying Hooke's law. Here's Hooke's law. You go, what does this have to do with duck walking? You'll see. So Hooke's law then is writing it out. We're almost done here. Fs equals negative kx. And this Fs, there's also a dance that goes with this called the spring dance. We'll practice this on the West Lawn, and then we're going to have a prom on May 1st. You may not know this. There's a prom on May 1st, but it's going to be at the stadium, and you're going to walk around and do stuff and wear nice clothes. I don't know what's going to happen. But anyway, we'll do the spring dance there. This is the force. This is the spring force. This is the stretch or compression of a spring. This is the stiffness or the spring constant. Spring constant. And I'll try and remember to bring some springs on Monday. We talked about it in class, but spring constant measures the stiffness of the spring. How stiff is it? Stiffness of spring. Like a typical spring, like a slinky, it's got about a K of around 50 newtons per meter. A I have different springs. One's 100, one's 1,000. One a rocker arm and a car engine, that's around 10,000. And then we have like truck springs, they're about 1,000,000. So you get really big K values. And this negative makes it a restoring force. It's a category of forces in physics called a restoring force. Okay, so we're going to use springs on Monday to stretch. We're going to stretch springs, attach it to the front of carts in the hallway, and that stretch spring is going to put a force on that cart and cause the cart to accelerate. So some springs will be stretched this much, some springs will be stretched this much. The more we stretch them, as Hook proved, and this is actually a lab we do in AP physics, the more you stretch that spring, the more the force. As the force, so the stretch. And so it's cool because they knew about springs before this, but no one understood the physics of it. It was Robert Hooke that measured and measured and measured day after day after day in the basement of the Royal Society, and finally got credit for something. It's the only thing he's still known for credit for. It's one of the probably 100 things he did. But Isaac Newton erased his memory, erased most everything else about him that he could, because Robert Hooke slighted him when he was 21 years old. How about that for pettiness? Okay, I mean, I love Isaac Newton, and I think he's a jerk at the same time, but he was one of the greatest thinkers ever. All right, so we're going to stop there, but that gets us set up for Monday. All right. So the homework then, just to put that up there, I should always put this up. For you all, it's just to finish 5.8 for the in-class kids if they're watching this. 5.8.5, 3 dynos, Monday. Any questions? Oh, I put it up there and you didn't see it. Oh, well, you heard what I said. 5.8.5, 3 dynos, Monday, and also watch the Silent Help video. Any questions from today? Anybody? You guys are free to go. Have a good weekend. I'll see you Monday. Adios. If you want to stick around and ask questions, now's the time to do it.
Mr. Askey,
Yeah.
so on number 6, could you explain that again for me? Because I didn't really get it.
Number 6.
Yeah, on 5.8.
Mm-hmm. You get that part? Oh, you can't see the screen. Let me get the screen back up. No, I'll go ahead and keep recording this, I guess. Okay, we're just repeating a little bit, but going over it again. Probably a good idea. All right, so feel that. Come on, man. Oh, here we are. All right, CD, does that make sense, that part?
Sort of, but I'm just wondering how you got the PAI plus PBI equals BAF plus PBF.
That's just that. All that is a conservation momentum. Summation of PI equals summation of PF. This is the summation. This is the summation of the momentums to begin with, and that equals the summation of the momentums to end with. And so then I just said, well, okay, if that's the algebra, I'm just going to solve for PBI, which means I move PAI over here to this side. And for some reason, I have it set up that way. I don't like that. I'm going to change it this summer so that PBI is on the left and these 3 are on the right. But it's still the same equation. So that's where I got that. Does that make sense? Conservation of momentum.
Yeah, it does. Thank you.
Okay, and then once you do that, then it's all head to tail after that. Does that make sense then? What any part of the head to tail doesn't make sense?
No, it's good. Thank you.
Okay, all right, you bet. Okay, so sharing, and I'll see everybody Monday.